In this session, it is with the model 4, and the topic is of notches and wears. In the previous sessions, it is covered with the orifices and mouths. Both are nothing but the measurement of fluid flows, and this notches and wear is also used for measurement of the fluid flow. So let us see that what exactly the wears and notches are concerned. So both are same, but only the dimensions will count. Let us first talk about the notches. The notch is nothing but an obstruction over which the flow of liquid occurs, as the depth of the flow above the base of the notch is related to the discharge. The notch form a useful measuring device. In case of measuring tank or reservoir, the opening is provided at the side of the tank such that the liquid surface in the tank is below the top edge of the opening. In fact, this is a large opening which has no upper edge, so that it has a variable area depending upon the level of the free surface. Now, on the other hand, let us see that what exactly the wear is there. A wear is a notch, okay, but on a larger scale, used for measuring the flow of river or canal, etc. It is a concrete or a masonry structure of substantial breadth built across the river in the direction of flow. This allows the excess water to flow over its entire length to the downstream side. Thus, a weir is a similar to small dam constructed across the river, with the difference that the excess water flows downstream only through a small portion called spillway, or in case of weir, the excess water flow through entire length. You can see that here in the figure, both notch and weir, we can see it in the same picture, but thing is that only dimensions is count. So now in this notch or a weir, so whatever the water is flowing, so here it will form a nap. You can see it in the other picture where the nap is the flow, whatever the fluid is there. So it's appear like a sheet of a water flowing through a notch or a oar. It's whatever it is called as, it is a nap or a vein. So whatever the figure you can see it, it's a nap or it's a vein. The bottom edge of the notch or the top of a weir over which water flow is known as sill or a crust. You can see it in the figure. The height above the bottom of the tank or the channel is known as the crust height. You can see that the crust height h is shown in this figure. Now let us see that in the previous sessions we have seen about the orifice, mouthpiece, all those things. Let us see some differences what we can notice. You can see it in the figure. You can see in the figure it shows the first one is the orifice. That is nothing but the orifice is an opening provided in the side or a bottom or the vessel of the tank, so that the fluid flow through the entire orifice. But on the other hand, you can see it in case of the notch is concerned. Notch is an opening that is provided in the side of the tank or the vessel, such that the liquid surface in the tank is below the top edge of the opening. So that we can see between the orifice and notch. Now at the same time, what exactly the difference between the notch as well as the weir is concerned? A notch may be defined as an opening provided in the side of a tank or a vessel such that the liquid surface in a tank is below the top edge of the opening. You can see that the position of the water level and how this nap is going to appear. And on the other side, you can see it, the weir. So weir is also a regular obstruction in opening stream over which the flow takes place. So you can see the notch and weir, there is no much difference, but only the size, whatever the size is there. Now, how this classification of the notches are made? So these notches are classified based on the shape. You can see that rectangular notch, triangular notch, trapezoidal notch, or the stepped notch is there. And you can see that in the rectangular notch, the first one. So here its dimensions like h, and water height is h. And as far as the discharge is concerned, because this notch is used for measuring the fluid flow, so that is the discharge. So that discharge is given by, for a rectangular notch, is 2/3 of CD into L into square root of 2 into G h raised to 3/2. So if you know the dimensions of L, that is the length of the notch, and height of the whatever the water head or a water height is available. So, and if you know the coefficient of discharge, so we can easily find out the discharge. Now look into the triangular, second one, triangular shape. You can see the triangular shape, and in this triangular shape, as usual, h is the water height and theta is the angle, whether it is a rectangular triangle or it is other type of the acute angle triangle. So depending upon the theta, so the type of the triangle shape is going to be appear. Then according to that, based on the angle made, so theta, so based on that, the discharge is calculated as Q is equal to 18/15 into CD into square root of 2G into tan of theta/2 into h raised to 5/2. So knowing the theta and the h and the CD, the discharge of a triangular shape, the discharge can be calculated. Now look into the trapezoidal, third one. It looks like obviously the trapezoidal shape will be there. The bottom length is L and the height of the whatever the fluid is available h, and the whatever the sides angles are to be defined as the theta/2. So here there will be the total discharge in a trapezoidal. We can say that Q1 and Q2. One is with respect to the rectangular notch, okay, the Q1 central one, and remaining side are of triangular. So that's why whatever the discharge of rectangular and whatever the triangular, the discharge is there. So that is summed up over here. You can see it in the trapezoidal, the total discharge is equal to discharge because of the rectangular shape notch and the discharge because of the triangular shape notch. Then whereas here CD1 is belongs to Q1, that is rectangular, and CD2 is the whatever the discharge for the coefficient of discharge for the triangular. So depending upon the shape, the CD is going to vary. According to that, CD1 and CD2 is there, so that the total discharge is sum of the rectangular plus triangular. Now sometimes this particular shape is also a stepped on. You can see that the stepping is made at the sides. So the first, whatever the short bottom side is, their length is L3. As it is increases, L2. Again, next step is L1, width is there. And similarly, the height steps are there, H1, H2, S2, whatever the heights are there, according to that H1, H2 and S3 is there. Now, whatever the discharge is there, so different rectangular pieces are there, according to that Q1, Q2, Q2, three steps are there. Q1 first step, Q2 second step discharge, Q3 third step discharge. And if it is a Q4, Q5, whatever the n number of steps are there, like that, the Q1 to Qn discharge will be there. Then total discharge will be nothing but sum of all the whatever steps are there, different steps are there, rectangular, the whatever the steps are there. So that is the total discharge. Next is a classification of the wear. Obviously, there is no much difference, as I told you that only the shape and the size looks almost similar. Only the size is a larger one, so that's why it is called as the wear. So here in the rectangular shape is concerned, the whatever the length is there, it's L, and height of the fluid is H, and as usual the discharge is given by Q is equal to 2/3 of CD into L into square root of 2G into H raised to 3/2. And similarly for the triangular, again it will be same whatever we have seen in the notches, same equations, same formula for the discharge is there. Theta is the angle and H is the fluid height, so that we can find out the Q is equal to 18/15 into CD into square root of 2G into tan of theta by 2 into H raised to 5/2. Now again the trapezoidal shape, yes, as usual here the two discharge will be there. One is a rectangular L and height H, so that is to be considered as a Q1, and whatever the theta 2 other side, both side the triangle, half triangles are there, so that one will be the Q2 discharge. So again the both, if you will sum up both rectangular as well as the triangular, you will going to get the total discharge for the trapezoidal system is concerned. Now here we are having the other further classifications is based on the nature of the flow. So nature of the flow, in the sense, first figure you can see that free flowing weir. So in the free flowing weir, so the liquid level on the downstream side is lower than the crust. You can see that whatever the downstream side, the level of the fluid is there or liquid is there, so it is a lower than the crust, so that one is called as freely flowing. And the second one is a drowned weir. In the drowned weir, you can see that the liquid level is submerges the crust, whatever the crust is there, okay, the sharp edge crust, so it is going to merge. So like that it has been classified based on the nature of the discharge is concerned. Next one is based on the width of the crust. So again it is classified as sharp crusted weir and broad crusted weir. In the sharp crusted weir, the crust is a narrow one, whatever the crust is there, it's a narrow one. Whereas here in the broad crust you can see that whatever the crust is there, okay, so the top edge of the whatever the weir through which the water is flowing, so it is in broad shape, so that's why it is called as the broad crusted weir. Next one is the chipolati weir or the notch weir or notch, chipolati weir or chipolati notch. So chipolati is nothing but the weir is of a trapezoidal shape, and where the side of the slopes are 1 to horizontal. You can see that whatever the slopes are there, 1 horizontal to 4 vertical, 1 horizontal to 4 vertical, whatever in the figure it shows. The speciality of the chipolati weir is that it is the whatever the horizontal is there, and 4 times the vertical, That's why you can see that one it is horizontal and 4 times vertical, so that's why it is h by 4. You can see that the whatever the width is there, h by 2, h by 4, and here the whatever the triangular shape is there, so theta by 2. Length at the bottom is L, and h is the total height of the fluid which is available. Now let us see in this figure. So here the whatever CD is there, bottom length L, and the height is fluid is H, and this particular AB and FE is based on 1:4, so that's why it is H by 4. Now let us see some equation to be arrived for the discharge. So that's why whatever the tan theta by 2 is there, it's nothing but the sides of AB by BC. So AB is h by 4 and BC is height h. So it will be tan theta by 2 is 1 by 4. According to that, if you consider theta, then it will become 14 degree 2 minutes, whatever the theta is there, theta by 2 is there. So now whatever the discharge is there, so we can for the Tripolity weir, for this case of the combinations of theta, length, h, so we can put it as discharge equation as 2/3 of CD into L into square root of 2G into H raised to 3 by 2. So this is all about the discharge of the Tripolity weir or the notch, whatever the Tripolity weir or notch, the discharge is defined like that. So now based on the whatever the shapes of the notches or weirs, so different classifications we have seen. So let us see the one by one, the whatever the numerical whatever the examples are there. So here let us take the example is like determine the flow rate through a rectangular notch if L is equal to 0.2 meter and H is equal to 0.15 meter and the CD coefficient of discharge is 0.645. So here it is said that what will be the discharge. So anyway, for the rectangular case, the Q is equal to 2/3 of CD into L into root 2G into H raised to 3 by 2 is there. Now just substitute the values of CD, L, both are the whatever the length and heights are in meter, no need to convert it, you substitute as usual. And anyway, G is by default is 9.81 meter per second square. So after that you can find out the Q as discharge as 0.022 meter cube per second, or if you want to put it in terms of liter per second, just multiply by 1000 to this value. Okay, so this is about the rectangular example. Now let us take the other type of the example. So here other type of example is nothing but determine the flow rate through a triangular notch if H is equal to 0.2 meter and the value of CD is 0.85 according to this equation of the triangular notch or a weir. So we'll be having Q is equal to 8 by 15 into CD into square root of 2G into tan of theta by 2 into H raised to 5 by 2. So here whatever the condition is there, according to that this theta is nothing but the 60 by 2, theta by 2 is 60 by 2 and H is 0.2 meter. So we'll be having the CD is equal to 0.85 after substituting this. So we'll be having the discharge as 0.0207 meter cube per second. So this is the examples for the rectangular notch is concerned. Now let us take another type of the example. Again it is a rectangular one, rectangular weir is there. Of course weir and notch, both the cases the formula is remain same what we have noticed. So just it is a weir's a little bit dimension is more as compared to the notch. So here it is a rectangular weir whose length is 0.3 meter and height is 0.25 meter and it is said that take the coefficient of discharge CD as 0.95. So whatever the discharge equation is there, 2/3 of CDL into root 2G into square root of H raised to 3 by 2. You substitute CD value, L value, as well as H value, and G value as 9.81. So after multiplications to this, the discharge works to 0.105 meter cube per second. So this is the other example. Now let us take the other type of the example. In this example, it is a rectangular notch. Rectangular notch is given, and where the whatever the notch is of having 40 centimeter in length long, and is used for measuring a discharge of 30 liters per second. An error of 1.5 mm was made while measuring the head over the notch. Calculate the percentage error in the discharge. So instead of taking the exact height, so it is taken as 1.5 mm error is there. So let us see that how this percentage error is to be calculated as far as the discharge is concerned. So let us see that L is equal to 40 centimeter length of the notch. Discharge is given as 30 liters per second. You can convert in terms of meter is just divided by 1000. Just multiply by 1000, and if you want to make it the centimeter, so it is to be multiplied by the 1000, so that we'll be going to get so much of meter cube per second. Now whatever the discharge error is there, so head is there, so 1.5 dH, you can convert in terms of centimeter, 0.15 centimeter, and the CD is given as 0.6. Now as far as the rectangular notch, the discharge equation is given by Q is equal to 2/3 of CDL into square root of 2G into H raised to 3 by 2. Now all the CD is known, L is known, and the H you supposed to be get it from this equation. You substitute all the values, and the G is to be taken as 981 because it is centimeter per second square. So now H is the only one unknown, so after substituting all the parameters like Q, L, C, D, okay, so G, then we'll get H is equal to 12.16 centimeter, and whatever the variation is there, so that error is to be calculated by this relation dq by q is equal to 2/3 of dh by h. So where dh is the error whatever it is measured, and h is the whatever the height of the fluid, and both the whatever the ratios of dh and h is known, so that we can have the 0.0185 is the ratio, but it is multiplied by 100, so we will get 1.85 percentage. So that much of percentage variation is made because of there is an error of 0.15 centimeter. Okay, this is all about this example. Now let us take the other type of the example. It is related with the right angled V notch is concerned. Whatever the right angle means, the theta, whatever the right means, right angle means theta is of the V notch is 90 degree, is used for measuring a discharge of 30 liters per second, and there is an error is noticed of 1.5 mm, and as made the measuring the head over the notch, calculate the percentage error, take the discharge coefficient discharge is 0.62. Whatever earlier example was there, it is related with the rectangular, so now it is a triangular V notch is there. So let us note down the points, the given things. Theta, rectangular notch is there, that's why theta is equal to 90 degree. Discharge is given as 30 liters per second. You just multiply by 1000, so that you will going to get so many centimeter cube per second. And there is error again, it is 1.5 dh is there, convert in terms of centimeter, 0.15 centimeter. CD is known, 0.62. So the whatever the discharge equations for this triangular notch is given by Q is equal to 8 by 15, CD into tan of theta by 2 into root 2g into h raised to 5 by 2. So in this case, discharge is known, CD is also known, theta is known, g is known, h can be only we can identify the head over the V notch, h can be identified. So now substitute everything over here. Yes, all the h, so you will get h is equal to 21.11 centimeter. So this much of the h we can get. Now as per the percentage error of the discharge, so the dq by q is equal to 5 by 2. For this triangular it is 5 by 2 dh by h. So according to this, you will be having the 5 by 2 and dh is known as 0.15, h is 21.11 centimeters. So whatever these ratios, you will going to get as 0.01776, and if you want in terms of percentage, it will be multiplied by 100, you will going to get 1.77. that is a percentage error. Now let us move into the other type of the example. So find the discharge over a rectangular weir, and the length is 100 meter. The head of the water over the weir is 1.5 meter. The velocity of the approach is given as 0.15 meter per second, and the whatever the coefficient of the discharge is CD is given as 0.6. and based on the available data, so we'll be having length of the weir L is 100 meter, and the head of the water H1 is given as 1.5 meter, and velocity approach VA 0.5 meter per second, CD is 0.6 is there. Now according to that, whatever the additional head which is going to form because of this, so it will be h is equal to v square by 2g. So whatever the velocity head is available, additional head can be calculated as v square by 2g. Substitute here both v as well as g, so you will get the additional head as 0.0127 meters. Now after that, let us find out the actual discharge which is going to happen because of the velocity approach. So according to the velocity approach, whatever the discharge is there, that is q is equal to 2/3 of CDL into root 2g h1 plus ha, that is additional head, raised to 3 by 2 minus ha raised to 3 by 2. Using this equation, so we will be having CD is known, length is also known, h1 is there, g is there, additional head ha is also there. Substitute everything, then after simplification, here you will going to get the discharge as 329.35 meter cube per second. So that is a discharge for this type of the case with the velocity approach is concerned. Now let us see the other type of the numerical example. So here it is a sharp crested rectangular weir, so which is of having 1 meter height extent across the rectangular channel of 3 meter width. If the head of the water over the weir is 0.45 meter, calculate the discharge, consider the velocity approach, and the CD is given as 0.623. So based on the data, so let us see that the width of the channel or the length is given as the 3 meter B, height of the weir is 1 meter, and head over the weir is h is 0.45. Now the total, whatever the depth of the channel is nothing but height of the weir plus whatever the head of the water over the weir, both the whatever the heights, if we consider, then only we will going to get the depth of the channel over here. So that is 1 plus 1.45, that is 1.45. And anyway CD is given. Then according to the velocity approach for the rectangular weir is concerned, q is equal to 2/3 of CD into B into square root of 2g into h raised to 3 by 2. So here CD is known, B is known, G is known, and also the whatever the head is known. So you substitute everything, so discharge, so we can get it. Now, as far as the velocity approach, the VA is equal to nothing but discharge divided by area of the channel. So discharge is known, is calculated Q, and whatever the area of the channel is nothing but the rectangular is there, it's a length into width, or width into depth of the channel. So substitute width as 3 meter, depth as 1.45, discharge as 1.665, so that we'll get the velocity as 0.382 meter per second. That is a velocity, approach velocity. Now the whatever the velocity approach is there, according to that we can find out the head available due to the velocity approach. It is nothing but v square by 2g. Substitute v as well as the g, so you will going to get the head due to the velocity approach is 0.0074 meter. You can get it from this calculation. Now according to this velocity approach, now the available total discharge is given by 2/3 of CD into B into square root of 2G into H plus HA raised to 3/2 minus HA by 2. Whatever the heads are, the two heads, velocity approach head and actual head, both are H and HAs are given, and as well as the G is also known to us, width is known to us, CD is known to us. Substitute everything so that the discharge with the velocity approach we can calculate it as 1.703 so much of meter cube per second. So that is the velocity approach discharge is concerned. Now let us take the other the whatever the last type of the weir or a notch. We have seen that it is a Chipoletti weir. So let us take the Chipoletti weir of the crust. Length is 60 centimeter, discharges the water. The head of the water over the weir is 360 mm. Find the discharge over the weir if the channel is 80 centimeter wide and 50 centimeter deep, and the CD is 0.6. Then based on this, the whatever the length of the weir is given as L is equal to 60 centimeter is there. Make it in terms of meter, that is 0.6 meter. Head of the water is 360 mm is there, so you convert in terms of meter as H is equal to 0.36 meter. Then channel width is 80 centimeter is given, so that one is to be converted as 0.8 meter, and the channel depth is there, that is 50 centimeter. Again it is converted in terms of meter as 0.5 meter. Now the cross sectional area of the channel for a this case is length, that is a width, into the depth, so that is 0.8 into 0.5, so you will get 0.4 meter square. So that is the cross sectional area of the channel. Now from the velocity approach, the first the whatever the discharge is there, so over the weir is given by 2/3 of CD into L into root 2G to H by 3, and according to the velocity approach, whatever the V is VA is there, so we can write it as a Q divided by A. So here first of all you just find out the Q is 2/3 of CD is there, L is there, G is there, H is there. According to that we are going to get as discharge as a 0.2296 meter cube per second, and if the velocity approach, according to that the VA is calculated as discharge divided by area, cross section area of the channel, so it is 0.2296 divided by 0.4, so you will get 0.574 meter per second. So that is about the velocity approach is there. Now with this velocity approach, available head HA is v square by 2g, so V A is there and G is there. Substitute it, so that HA is calculated as 0.0168 meters. Now according to this velocity approach, so the discharge is given by Q is equal to 2/3 of CD into L into square root of 2G into H plus HA raised to 1.5 minus HA raised to 1.5. Substitute CD, L, G, H is there, HA is there. After simplifications, the discharge due to the velocity approach is given as calculated as 0.2435 meter cube per second. So this is about how this velocity approach discharge is calculated. Now moving to the other part of the wears and notches. So here the ventilation of the wear, you can see different figure, whatever you can see it here. So what exactly the ventilation of the wears is that? So the whatever the air is there, so he is carried away by the flow of the water, so which results in creating a negative pressure beneath the nappe. So whatever the below the nappe, so there is a negative pressure is going to create. So the negative pressure drags the lower side of the nappe towards the surface of the weir wall. So you can see that initial nappe, so it is the whatever the negative pressure is there, and when it is further depressed nappe, and here again it will become the clinging nappe. Okay, so whatever the ventilated holes are there in the wall, and whatever the shape is there, you can see that so according to this the whatever the negative pressure is there, so it drags the lower side of the nappe towards the surface of the wall, and this result is more discharge than the normal discharge. So holes whatever it is there, so that the holes are there, so that is called as ventilation of a weir. So whatever these holes are there, so this one is to maintain the discharge proper. So what is there, so the some holes are provided, so that's why such holes are called as ventilation of the weir. So ventilation of the weir, so that we can see it here with this figure. Now next one is the submerged weir. So here the whatever the weir is there, so it is submerged. You can see that whatever the left hand side and the upstream side, left hand side, right side is a downstream side. So because of this submergence, there is a variations in the head is there. Initially it is h, and later it become h, and difference in head is h by h. So whatever the height of the water is there, h on the upstream side of the weir, that is a capital H, and small h is nothing but the height of the water at the downstream side. Now here based on this, so we'll be having the discharge equations. So we'll be having the discharge equations for the Q1, that is the upper stream portion, or the upper stream portion, and that one is called as 2/3 of CD1 into L into square root of 2G into H minus 3 by 2. And one more is the discharge Q2, that is a downward portion. Downward portion is CD2 into area of the flow into velocity of the flow is given by CD2 into L into H into square root of G into H minus H. So whatever the total discharge, we can have the Q is equal to Q1 plus Q2. So Q1 equation you substitute, Q2 equation you substitute, so that the total discharge over such cases for the submerged weir can be calculated. Submerged weir can be calculated. Now let us see the same one example over here for the submerged weir. So that the height of the water on the upstream and downstream side of the submerged weir is given as the 3 meter length with 20 centimeter and 10 centimeter the height variations. If the CD is free and drawn portions are 0.6 and 0.8 respectively, means free case it is 0.6 and drawn portion it is 0.8 respect. Find a discharge over the weir it is there. So now here some dimensions are in terms of centimeter, just convert it in terms of meter. So according to H is 20 centimeter is there, 0.2 meter, and the drawn side H is 10 centimeter, so that is the 0.1 meter, and length is the 3 meter, and CD1 and CD2 are 0.6 and 0.8. Now based on the available equations, so we'll be having total discharge is calculated as the sum of the two cases of the discharges, okay, free portions and the drawn portion. So according to that, Q is equal to 2/3 of CD1 into L into square root of 2G into h minus h raised to 3 by 2 plus CD2 into L into h into square root of 2g into h minus h. So you will be having CD1 is there, CD2 is there, length is there, h and h both heights are there. So you just substitute all those things, and finally you can have the total discharge because of this submerged case of the weir is calculated as the sum of the two heads. So that is 0.504 meter cube per second. So this is all about the weirs and notches topic. So with this, the model 4 topic is over. Thank you.